Hi, welcome to another PlayBASIC live little video. The other day I posted an example that has a look at array wrapping or filtering, and it goes through a bunch of different methods on how to speed that up. In the filter itself, in the naive version of the code, we're running through and it's a two-dimensional array. We're looking at each cell in the array and all of the cells around it, and then just averaging them out. So we're reading every cell 9 times as we go through. So there's a lot of extra overhead in just the naive version here. So it's on the forum here, it's in the source code section, log in to see it. We'll go down to the version I was writing the other day. So the two-dimensional array is 500 by 500, so we've got like 250,000 cells in this array to really give it a bit of a headache when we're trying to do this stuff. The test code itself is just calling a function. It's making the function name, because the functions themselves, the test functions, are just kind of given funky names to average array 1, average array 2, so I can just have a bit of code dynamically work out what's going on, call each version. So this is the stock standard way you sort of see this stuff. We're running across the array and over every cell within that two-dimensional grid. Then we're looking at all of the cells around it, and including itself, adding them all together, and then dividing it by 9. So already you can kind of probably see some optimizations in that because there's a possibility that our coordinates will move off the end of the array, off either, because we're stepping from along the x-axis here. We're starting at the current position along the x-axis, we're stepping back 1, and we're stepping ahead 1. So if x loop was 0, we'd be trying to access a coordinate of -1, which is an illegal, and you'll get a runtime error. So we have to wrap these coordinates here. What we really want it to do is not get the one that's at -1, we want to get the one that's on the other side of the array. Same with the vertical one. So this is the slow, naive code. That's just left over there from I was cutting both. That's same as that, it's just leftover junk. So the second version takes a look at this problem. It gets rid of most of the wrapping internally. So we compute the row above our current row and the row below our current row outside of the X loop, so they never change inside that X loop. Gets rid of a whole bunch of wrapping that would occur inside the loop. We're running across the row. We're still doing our X here though, but we're wrapping this once and then just using that coordinate. So we've got 3 wraps per pixel, and we're still accessing each point on the array 9 times. So if the array has 1,000 cells in it, then it's 9,000 accesses just to do the 1,000 cells. So as it gets bigger and bigger and bigger, it's a massive amount of overhead for nothing. But even so, this one here is a much faster routine than the straight naive version 1. Version 3 will get a bit more complicated. We've got 2 loops. We've got a version of the filtering routine without any wraps in it at all. Sorry, it wraps the y coordinate to be convenient, and then just does the although it doesn't need to do those at all actually. So we know that if we move from the 1 coordinate to the width of the array -1, we can never have any illegal array access. So we can just get rid of those wraps internally. And then we've got a second version of the loop that only handles the edges. So they use wrap as well, but we're still accessing each cell multiple times, more than what we need to. The versions at the bottom, here we have an unrolled version of that code. Got rid of the loop. We just unroll exactly what it's meaning to do, so it's becoming less and less flexible, but faster and faster. It's the same process as the one above it, but that's we've got a 2-pass loop. We're doing all of the ones that don't need any coordinate wrapping with the streamline inner loop. Then we're doing the outside coordinates with kind of a slower, clumsier version. And the last one, this one actually tackles the problem of how frequently you reread the coordinates. What's normally happening up in these other ones is we've got this kind of array. I'll just make a very small array. So these are our values in the first across the row, you know. Let's just pretend all the rows are all the same. Okay, so when we do this filter, we would normally be looking at this coordinate here when we start, and we're doing the average of all the cells around it, and we wrap the coordinates around. That means we're reading this cell plus 9 cells around it, which gives us 9 cells. When we move to the next one, we're doing the same thing, but we're rereading the stuff here. So what we could do is we could run across the row and pre-compute each cell here. We'll just add this one, and that one, the 3 here. Do it for the next 3, so on. What that helps us do is actually, we've still got those 3 additions for each coordinate, but as we step down and go row by row, we only have to compute those once. So I'm sort of, as we go through this this version of the array, we're preloading the very bottom row from our source array into. We've got 3 arrays here that are one-dimensional of that width. They're floating point, because the array we're averaging is floating point. We've got the row that's above the row we're currently scanning across. We've got the current row and the next row. So what we have to do here is we precede the previous row and the current before we start the loop. And then inside the while loop we grab the next row. And since what that tally does is it adds itself to the one before and the one after it, we only ever do that once. And then we run through and we tally up the three rows, and we swap the arrays, swapping the flip. So the previous row becomes the current, and the previous row becomes the next. Yeah, because that. So previous is swap with current, and then we have to swap previous because this is now current. Probably not making much sense. Anyway, let's have a look at the demo. I don't know how it will capture. Probably pretty poorly. It won't capture with that stuff there in it, that's for sure. It's a bit of garbage. Just running this on the HP all-in-one Celeron system, so it's not particularly fast. So this is the naive comparison. We're doing 250,000 samples. That's 250,000 by 9 samples in these first couple of tests. So we're improving the logic as we go through, and then the last one strips away more of that logic. Okay, so the initial test was 640 milliseconds per pass. Just by rearranging the logic, we'll get that down to 237. And as we keep rearranging that logic, it comes down to 180, 150, and the last one we're down to 100. So it's basically 6 times faster than the naive version without much effort. But it's a good technique to wrap your head around in particular. It's this kind of pre-caching, and it gives you a bit of understanding as well about the passing arrays in PlayBASIC and doing things like swap arrays. Swapping the array contents it changes by a pointer, so there's no data being copied when this happens. We're just swapping the 2 pointers and then life continues on. Anyway, that's what I wanted to look at. So hopefully it gives a bit more insight into this kind of idea. Filtering like this occurs a lot of different places. Just trying to think of one. I think the Game of Life, actually. If you remember that old, not actually a game, it's like a little simulation. It has a very similar kind of concept where you run through an array and you read the current point and then all the points around it, and then depending what they add up to, you take some reaction. I can't think of the rules off the top of my head, but I'm sure if you Google Game of Life, you'll come up with it. There might actually be one on the forum. Jeez. Oh, I can't remember now. I got a feeling someone made one on the forum, so maybe do a bit of a search for that. If you're bored one day, a bit of entertainment. So okay, that's all I wanted to chat about just now, and of course you can find the full code on the boards. And if you have any real sort of questions, we'll get in the forums and ask them. That's how we learn. The code that draws the array is pretty ugly. We're just running through the array and drawing each point as a color, kind of grayscale color. Just out of curiosity, so we're running with a 500 by 500 array. Let's do it on a 100 by 100 array. So what we get. Oh, I probably haven't bothered. Yeah, I haven't bothered to do that. Okay, I'll go. Right, so even the naive version is actually fast enough to do a reasonable blur. That's what the algorithm here is doing, by the way. It's doing a color blur. Okay, so for 100 by 100, which is 40,000 cells, we're down to 17 milliseconds. Pretty reasonable. What if we did something crazy and went up to 1,000 by 1,000? Probably pushing it now. Yeah, so that first version, that average array version 1, that's the naive base code. So looks like it's taking a few seconds to get through that many cells, but that's over 1 million cells. So each cell is being read 9 times, so it's 9 million axis. And you got some write axis there at the end too. So already the second version is ticking away at probably about a second or so per revision, maybe about a second and a half. Getting down to that second mark. Actually, all you want to do is you want to blur an image. By the way, just use blur image; it's built in. It's much easier than just doing this stuff. But if you need to, you can. It's worth actually taking a bit of time and learning this stuff. Okay, there's got some massive numbers there. 2.5 seconds for the naive version, and the optimized version's 436 milliseconds. So that's still in that 5 to 6 times faster ballpark. All right, that'll have to do. Go and have a bit of fun coding, and I'll catch you some other time. See ya. Bye.